Okay, so we're working on worksheet number 8 today, and worksheet number 8 is our first worksheet in what we would consider our metabolism unit of the course. And metabolism is a complex subject, as I'm sure you are finding out, and in chapters, for instance, 11, 12, 13, and 14, we're going to be looking at the specific details of how carbohydrates and lipids are going to be broken down, catabolized essentially for energy needs, in particular the production of ATP. Okay, so, and there's going to be lots of metabolic pathways, going to be lots of details, and those details are very important. Okay, now having said that, there are going to be some things that I would like students to walk away from this class in terms of larger picture. Okay, some central concepts that I think are really important for you as a student to understand metabolism. And so I want to spend some time on our next couple of worksheets looking at some of those larger picture concepts so that we can have a better understanding, and that you can have a better understanding of metabolism. Okay, and one of those things that I really want students to recognize is, and to walk away from this class with, is an integrated view of metabolic pathways. Okay, meaning that there's lots of details in metabolic pathway, but those details start to make sense when we start to see how they're all integrated one with another. Okay, and that's a lot of what we're going to be doing today. We are going to be actually looking at, okay, let me get rid of this. Okay, we're actually going to be thinking about this reaction here, okay, which we talked about in chapter 10, the production of glutamine from ammonium and glutamate. Okay, and this is a very important reaction. All right, let me make sure that my U over here, it does actually look like a U to everyone. There we go. All right, so we're looking at the production of glutamine from glutamate and ammonia, and this is actually a really important reaction in the cell. Certainly it's important from an anabolic standpoint. We have to make glutamine for the production of proteins that require glutamine in them. But at the same time, interestingly, when our cells catabolize amino acids, which many of our cells do, one of the byproducts of that is ammonia. And that ammonia, if it's secreted into the bloodstream, can be very toxic to us and very deadly. And so we actually, our bodies, our tissues will actually take that ammonia and place it on glutamate, making glutamine, and then they'll secrete glutamine into the bloodstream. Glutamine will be absorbed by the liver, and the liver then will remove that ammonia and safely put it on urea. And urea will be the thing that we excrete nitrogen from our bodies in. Okay, so a very important reaction. There's other reasons that it's an important reaction. For instance, if you get into neuronal tissues and you talk about nerve conduction, glutamine can play a very important role in that as well. Okay, we're not going to do that, but this is a very important reaction. Okay, and what we want to say with this is that we want to say, well, this is exergonic. Exergonic is inorganic, meaning that our delta G of this reaction is going to be positive. Okay, and so what we want to think about here in terms of the larger pictures is that this reaction is actually going to be coupled to or connected to, from both a material standpoint and an energetic standpoint, to a host of other processes going on in the cell. And that's the main point. When we think about metabolism, we need to think about how metabolic pathways are connected one to another either by materials or by energetics. Okay, meaning that when we think about it from a material standpoint, maybe one metabolic pathway provides the materials that the other pathway needs. Okay, so glycolysis will produce pyruvate, which is then converted to acetyl-CoA. Acetyl-CoA is then the initial substrate of the citric acid cycle. There's a material connection there. Okay, energetically speaking, we can think about ATP. The production of ATP is made by some catabolic pathways and then is used by many anabolic processes. So that's an energetic connection. Okay, all right. So what we want to do here today in both of our activities is think about the pathways that would need to occur, okay, and steps within those pathways that would need to occur both from an energetic and a material standpoint to get this process to occur. Now, we're not going to look at all of them, certainly. That would require us to look at many of the metabolic pathways that we're going to be looking at in upcoming chapters, but we're going to look at some of them, okay? And so your first activity gives you this whole list of steps in different metabolic pathways and different metabolic processes. And the question is, well, just determine whether those steps are either exergonic or endergonic, okay? So you can make essentially a table that would look like this. Okay, on this side would be endergonic. Okay, and on this side would be exergonic processes. All right, and so, you know, for instance, this step here is described in A, the one that we're looking at here. So we're going to give you a give me. It says glutamine is made from glutamate and ammonia. Give me. This is give me. This one is endergonic. Okay. And so what we could do is just say, okay, we'll put step A over here. Okay. And what you want to do is, of course, the rest of them all the way up through step G. Okay. All right. So pause it. Do that. Okay. And then we'll come back and look at this together. Okay. So I trust that you have paused it, that you've thought about those processes, okay, that you've made a table here and that you've put them there, and so I want to give you some feedback. And now some of these I think are really straightforward and fairly easy, okay, and you probably didn't take you very long. Some of them are a little bit more challenging. In particular, when we look at redox reactions, those can be a little bit more challenging to students, right? And when I say redox reactions, people are like, oh, get chills of excitement, right? So let's go ahead and look at this, and I'm going to go all the way to the last one, step G. Okay, and I want to think about, well, how can we look at this redox reaction and determine, is it exergonic or is it endergonic? Okay, and there are a couple ways to do this. There's the long way, which I'm going to show you first, and then there's a short way, which I'll talk about afterwards. Okay, but it says this is a redox reaction in which isocitrate is the electron donor and NAD plus is the electron acceptor. The half reactions are shown below. Okay, and so what I'm going to do with these half reactions, I'm going to turn them in the appropriate direction. So it says isocitrate is the electron donor. So let's go ahead and think about that. And I'm going to turn this half reaction then like this. I'm going to take isocitrate, I'm going to make that my reactant, and it's going to give up electrons, which means that electrons are going to be a product of it. Okay, and so I'm going to put them over here. And then that's going to make this thing called alpha-ketoglutarate, okay, and it's going to make 2 protons as well, and it's going to also make some CO2, okay. All right, but the main thing here when we say it's an electron donor, we're going to put the electrons on the product side, okay. Now the electron acceptor then is going to be NAD+, which means that I'm going to put NAD+ over here, and I'm going to have the electrons then being a reactant in this, okay, and that would then indicate that our NAD plus is our electron acceptor, okay, and that's going to make NADH and a proton. Okay, now understand that as we think about this, these electrons are coming from our donor, okay, isocitrate, so they're coming from up here. Okay, now the important part of all of this is going to be these reduction potentials. Okay, and so we're going to put the reduction potential of this is equal to negative 0.38 volts. Okay, and then the reduction potential of this is going to equal negative 0.32 volts. Okay, give the unit of those. All right, now how do we know whether this reaction, okay, and when we combine it, let's just go ahead and do that. How do we know whether this is exergonic or endergonic? So let's combine this. We're going to get rid of these. We're going to cancel these out. Okay, and what we're going to be left with is this isocitrate will react with NAD+, giving its electrons NAD+, and that will make then NADH, which will be reduced then, and alpha-ketoglutarate, which will be an oxidized form of a molecule, and CO2. Okay, and so that's our reaction as a whole, and I forgot my proton, so we'll have to put that there. There we go. Okay, so how do we know if that's exergonic or endergonic? Okay, and the long way to do this is to look at this reaction, this equation. Very accurate way of doing this, a little bit longer. Okay, All right, and there's our equation. And what we need to understand here is this, that the delta E is going to be equal to essentially the electron, or the reduction potential of our electron acceptor. So I'm going to just put EA here, right? And then that's going to be minus the reduction potential of our electron donor. Okay? And so when we do this, of course, we want to understand that this is going to be our electron donor, so we're going to put that here. And this is going to be our electron acceptor, so we're going to put that here. And so our reduction potential for this is going to be, or our change in the reduction potential, is going to be equal to essentially negative 0.32 minus a negative, put a parentheses here, 0.38. Okay, and what that means is that this is going to be a positive. You can do the arithmetic on your own, but it's going to be a positive 0.06. Now, here's the great thing about this. We can then plug that back up into here, and we know that that's a positive number. Well, with the negative sign in front of this equation, that means that if the delta E is positive, then delta G will be negative. Okay, and so this is going to be one of our exergonic processes, and so I'll just come back up here and I'll just say that step G is indeed exergonic, okay, because of all of this that we talked about. All right, now there's a couple of things that I want to mention here. Okay, first of all, some of you are saying, well, you know, you took this and you flipped it, and when you flip it, don't you have to change the sign on this? And the answer is no, I don't have to change the sign on that. The reason I don't have to change the sign on that is because this equation does it for me. Okay, it puts this minus sign here, and that's going to always change the sign on the electron donor. Okay, so I don't have to do that because that equation does it for me. Okay, so that's the first thing. The second thing is like, okay, yeah, I can see that. I understand this. But you said something about a short way. Is there a better way to do this? There is, I think. And the main thing that you want to do from all of this is take away this understanding of what do these values mean. Okay, these values mean that as we look at them, they have a particular affinity for electrons, okay? And the larger that number is, the stronger the affinity of electrons of that particular molecule. Okay, so for instance, NAD plus in this case has a stronger affinity for electrons than isocitrate and alpha-ketoglutarate because it's a larger number. And therefore, we would expect that any reaction in which NAD plus is taking electrons from the isocitrate molecule is going to be spontaneous because it has a stronger affinity for those electrons, and therefore it should be spontaneous, right? It has a stronger or greater ability to attract electrons to itself, okay? And so that's really what you want to think about. And I mean, you can do the arithmetic for it all, and that's fine, but you just think about affinities and say, okay, the one with the stronger reduction potential is the one that's going to lead to a spontaneous movement. Now, if we had flipped this around and said, okay, NADH is going to give us electrons to alpha-ketoglutarate, well, now we're having something with a stronger affinity for electrons give electrons to something with a weaker affinity, and that shouldn't happen spontaneously, right? That'll take some work to get done, okay? And that's the basis, actually, of photosynthesis, though we're not going to look at photosynthesis in this class, okay? Okay, now, the other things, we've got quite the list here. We've only got 2 things on our list, so let's just move through the list. The next one is an ion is moved from compartment B to compartment A, and it looks like compartment B has a smaller concentration of the ion than compartment A, though it's moving from compartment B to compartment A. So that then describes, and I'm just going to work my way backwards, by the way, that makes F, step F, right, something moving from a high concentration to low concentration, endergonic. Okay, that I think most of you understand. We spent some time in chapter 9, of course, talking about that. You've known these things for quite some time, I would hope. Okay, so F is endergonic. E is really simple because hopefully you've recognized that ATP is the fire molecule, right? And when it's hydrolyzed, good things happen. So we're going to put E over here in the exergonic column. Anytime ATP is hydrolyzed, it's going to give off energy, can do work, okay? Now, D is another one of these redox reactions, okay? And in this case, it says a redox reaction in which NADH is the electron donor, and ubiquinone is the electron acceptor. The reduction half reactions are below. Okay, ubiquinone and NAD+. Okay, so in this case now we have NADH is going to give its electron, so it's going to be the donor to something that we call ubiquinone. Well, when we look at NADH's reduction potential, it's still negative 0.32 volts, okay, as it was in our last time. But in this case, the ubiquinone's reduction potential, the electron acceptor, is 0.045, which is a larger number than negative 0.32. Okay, so this is describing a situation in which something with a weaker affinity for electrons is giving some electrons to something with a stronger affinity for electrons. In this case, stronger affinity for electrons is in ubiquinone. That's, again, going to happen spontaneously. Again, you can do the arithmetic there, but the larger reduction potential of ubiquinone relative to the electron donor, what we are stating as electron donor, NADH, means that this is going to be a spontaneous process or exergonic. Okay, so we're going to put D over here. Okay, and that's going to be a process in which NADH is made, and is used. In the last process, this one we had NADH being made spontaneously. Okay, all right. Now, C, ATP is made from ADP, an inorganic phosphate. Well, if you're going to get energy from ATP hydrolysis, making ADP an inorganic phosphate, then to make ATP from those things is going to cost energy. Okay, so we're going to have to do work to make ATP, so we're going to put that as an inorganic column. And we have one left, B. An ion is moved from compartment A to compartment B. Again, compartment A has a higher concentration of the ion than compartment B, so this is going to describe then exergonic movement of the ion. Okay, all right. So because of course we're going from a high concentration to a low concentration. Okay, and that's exergonic or spontaneous. Okay, all right. So now what we need to do here is we need to put these things in order, right? And that's our second activity. It asks you to put all these processes in order so that then glutamine can be made, right? So we want to say this. I'm going to go ahead and start you off here. We want to say that step A is the last step, okay? And we also know this. Well, we'll just leave it at that. Okay, we'll just say last step is here, A. And well, I'll give you one more. We have said in Echo 360 recordings, right, and in class, that ATP is needed to do that, right? So we're going to say E, ATP is hydrolyzed, and that's going to allow glutamine production from glutamate and ammonia. We've talked about that, okay? And so I'm going to go ahead and cross these two out, and I'm going to say, okay, you put the rest in order. And the key that you want to keep in mind is that these have to be connected energetically, and they have to be connected materially with one another. Okay, so pause it, try and put these in order, and then come back and we'll think about this together. Okay, so hopefully you pause it and you got a good order now. And so we want to think about this. And again, material and energetic connections is what we're going for here. Okay, and so what we have here is ATP being used to make glutamine from glutamate. Okay, and so obviously then I would hope it's obvious. Okay, the next thing that needs to, or the thing that has to precede ATP hydrolysis is the production of ATP. Okay, which is described in step C. Okay, so what we're going to do here is we're going to put step C next. C is ATP production that will lead to then, of course, ATP that can be hydrolyzed in E that can then be used to make glutamine from glutamate and ammonia. Okay, so that's how we have to think about that. Now, what we need to think about next is, well, that's an inorganic process, so we need to then have one of these exergonic steps being utilized to make, okay, the being used to make the ATP. Now, there's a couple of options here. We've got two redox steps, and then we've got, of course, an ion gradient that can be used. Okay, so we want to be careful though with our upcoming steps that we're going to have the materials and also the energy needed to do these things. Okay, so for instance, when you look at the two redox steps, and I kind of alluded to this when we were looking at them in our last activity, one of them makes NADH and the other one uses NADH. So those need to become back to each other, right? Because if we're going to use NADH, then we have to make it. Okay. All right, so that will be something we need to think about. We also need to think about then our ion gradient. If we're going to use it, we have to be able to make it. Okay, and so in this case, what we want to think about is the fact that we need one of these exergonic processes over here to provide the energy to make ATP, and it turns out that an ion gradient is a great candidate for this. Okay, so B, the ion gradient, can actually be used, as we'll talk about in chapter 13, can actually be used to make ATP. Right, so that's B. Now that means that then we have to have generated the ion gradient, F, okay, to then be used to make, of course, ATP. Okay, so F describes a process in which energy is input into an ion gradient, and then that ion gradient energy is used to make ATP, and then ATP, the energy stored in it, is used to make glutamine from glutamate. Okay, now our last two steps are of course going to be our redox reactions, and hopefully you know what order to put them in. And they're both exergonic, so they're not really connected energetically, but they're connected materially to one another. Okay, and that is this, that you have to have production of NADH before you can use NADH. So G is going to make the NADH, and then D is going to use the NADH. Okay, and it turns out that when we look at G, this is a process in the citric acid cycle, and when we look at D, NADH is going to carry electrons to the electron transport chain, and that's the processes of that we're going to talk about in chapter 13. Electron transport chain is going to be used to make an ion gradient, and the ion gradient is going to be used to make, right, and on down the list, is going to be used to make ATP. ATP is going to be used to make glutamine from glutamate. Okay, so you can see hopefully the material and the energetic connections here, and that's all just to make, you know, this fairly simple molecule. Okay, all right, so I'm going to go ahead and stop right there. Hopefully that you found this very helpful. Okay, and you can see the first law of thermodynamics in play here, and you can see how metabolic pathways are integrated one with another. Okay, both materially and energetically. Okay, all right, take care, everyone.